Yeah, so good morning, everybody. First of all, I would like to thank the organizers for inviting me. My name is Thomas Sübmeier. I'm professor at the University of Neuchâtel in Switzerland. And today I'm talking about especially high-power ultrafast oscillators and also some applications with them that you can do in the area of nonlinear science. So here you can see a picture of the city of Neuchâtel. We are located at the lake of Neuchâtel. This lake is actually the biggest lake in Switzerland. Okay, in Switzerland because, the lake of Genève and also of Constance, they are shared with other countries, so they don't really count. And so we are somewhat in the middle between Geneva and Zurich, so here in the first question, for the kind of pictures, it's okay, you can see something, or should we lower the stores? It's okay? Because of the video, okay. Yes. Okay, so, the time frequency laboratory at the University of Neuchâtel is about 30 people. We are 2 professors, and we have a focus in the development of, on one side, atomic clocks with high precision, with various techniques. On this I will talk tomorrow in the lecture about frequency comps, because this was one of the big revolutions that happened in the last decade. On the other side, we're also working on laser systems and various applications of them. So this is the focus that I'm giving today. So in my scientific team, we are about 15 researchers. Here's a picture of us skiing. You anyway can't see anything with a bright light, but on the other hand, well, at least you have a video afterwards that you can see, and probably there you have a higher quality of the pictures. Now, when I received the program for the spring school, I had 2 different thoughts. So the first thought was, this is quite incredible. I've never seen any summer, spring, winter, or whatever school where they managed to put that many talks in, even finishing every day at after 10. So that was the first thought that I had, and when I received it, I forwarded your email to the 2 PhD students from my group who are participating here. I even made a kind of joke about this. Well, at least you have the weekend of the 1st May to recover from all this. And then actually they told me that they wondered if I was making fun of them. Because on the 1st of May, despite being a holiday, you also have lectures. But then the second thought was, wow, this is quite incredible. The people that you get for this spring school, I mean, these are the people from whose book I learned nonlinear optics. So it's really a who is who in the area of nonlinear optics. And also when I then had a look at the different topics presented, I just saw that, I shouldn't go to the basics. I should more stick to the laser side. What's the point in me telling things about fundamentals in nonlinear optics or some other systems which are already presented? So you really have a great overview of the state-of-the-art researchers in various areas, and this is something which I then also will use now. You've already seen the foundations of nonlinear optics. Majid gave a presentation about OPOs and also solid-state sources and so on. So I will focus a little bit more on the things which I did in my research and give an overview on these areas. And here you can see the program for this morning. So I will start first with a discussion about ultrafast lasers. So far in the program, you didn't have anybody presenting something on ultrafast. Majid a little bit, but probably you didn't go too much into the details of the lasers. Afterwards, you will hear then quite a lot also about from Baltuska about the nonlinear sources. So Andreas, I think he will make a strong focus on this, also on the amplifiers and mid-inference sources. But so for me, this is then the starting point, giving a small introduction into the ultrafast area. Afterwards, I will talk about an area in which I've been working for quite some time, and that is the realization of high-power ultrafast oscillators. There are amplifiers, that's one category. There are oscillators, another category. And I will put the focus on the second one. And then I will discuss 4 nonlinear systems for which such ultrafast oscillators I think are quite interesting pump sources. The first one is on temporal pulse compression. Quite often you are limited in your pulse duration by the laser material that you have, and you can easily overcome this by using nonlinear optics. The second is frequency conversion. At the moment, nearly all the really good and cool and wonderful laser materials that you have for high power operation, they are based on ytterbium and they only operate in the 1 micron regime. And nonlinear optics is a great way to overcome this issue. And I want to illustrate this by just taking a system which combines a lot of different techniques, parametric generation, some frequency, second harmonic generation, and where you take an infrared beam that you can't see and you convert it into 3 different colors, red, green, blue. And the target at the time for this was to do laser projection. Then I will talk a tiny little bit about UV generation, something for which I think these high-power ultrafast oscillators will also be quite interesting. And finally conclude by going even one step further in the UV, going to the visible UV or the XUV by high harmonic generation. But this is just a small starter, giving a kind of taste of the whole area. You will get a great overview by Paul Corkum, one of the founders of this whole area. Okay, so let's start. Ultrafast lasers. Well, the first question when you hear ultrafast lasers is, what the hell is ultrafast? I mean, something is fast, okay, you can easily imagine, but ultrafast, what does it really mean? And I think for quite some time initially, people didn't even know it was something sexy, and ultrafast meant that you're more likely to get your grant through if you put the word in the title. But I think nowadays, the thing that is, I would say, a good definition is if you're in the picosecond regime or faster or shorter in terms of duration, so picosecond, femtosecond regime, attosecond regime, then you can claim that you're in the ultrafast world. So maybe in order to bring this into a context, so if we're talking about a femtoseconds, we are talking about 10 to the minus 15th of a second. Let's bring this in a slightly larger context. Fast for us humans means something completely different. So our eyes are actually quite slow detectors. If we have 24 images per second in a cinema, humans are not able to distinguish the individual images anymore. And so that means that we are very, very strongly limited in our resolution or in our speed of detection. And that means that simple events in nature are already too hard for us to understand. And one of the most prominent examples is the movement of a horse. So if you take the fast gallop of a horse, humans are not really able to see what exactly is happening. And there have been debates a long time ago if a horse during the gallop has at one point all of its feet off the ground. And here we can see 2 images from George Stubbs. So George Stubbs was considered the painter of the horses. So the first image here, Whistle Jacket, is from 1762. Okay, sorry, with the light you can't see the picture really well, but it's a nearly photorealistic image of a horse. And then he also tried to picture a horse during the gallop. And if you look at this, it's kind of awkward. So all 4 feet are off the ground, but the position looks somewhat unnatural. There is something strange, but you cannot really put the finger on it. You can't really say exactly what is happening because eyes are too slow. And one way to overcome this issue is to try to use other detectors. So I think the story was that Leslie Stanford more than 100 years ago, then had a bet or a prize for the person who could help to understand the problem, solve the question if the feet of a horse are off the ground. And then Mr. Muybridge in 1878, he used then fast photography, so mechanical photography, to resolve this issue. And so here the pictures that he took. What he did was quite simple, just had a couple of wires over the track and then individual cameras which had a mechanical shutter allowing for millisecond resolution. And so in the end he had then a sequence of 20 pictures or so, which are now mounted here one after the other. And you can see there is a point during which the horse has all 4 feet off the ground, but it's now. It's not when the feet are in opposite directions. And that's something which is not really intuitive, and that's where fast detection can help you to understand science. So with the mechanical shutters, at that time at least you were limited to the millisecond domain, hard to do anything better. What else can you do? Well, another possibility is that you simply leave your camera open but get rid of all the other light and use very short flashes of light to illuminate something. That was what Harold Edgerton did in the 19th. And he then took a great number of pictures where he could investigate things by using flashlight in the microsecond domain. So pictures which usually at that time you could not take at all. And for example, here you can see the movement of a tennis player, what exactly happens when you're hitting the ball. So here you can see the nice parabola of the ball thrown up to the top, and then the movement of the racket. Or another thing, here in this picture you can see what happens when a bullet goes through an apple. And it's something which is absolutely non-intuitive. If you would take an apple and a bullet and ask a physicist, how does it look like the moment right after the bullet went through? I think it would be quite hard from standard simulations of solids, liquids, and so on to come to this result. Also, it's quite astonishing to me, you have a similar result to both sides, even at the side where it entered, you have a similar skin texture and so on. But once you have such a result, you can start to develop a model. So you can start to define the skin, something that is inside. You maybe have then also an idea how long the different particles will be ejected and so on. So if you have detection, it helps you to develop your models. Another thing here, so apparently he liked bullets and shooting things, making explode things. So here is a bullet, and then he simply sent it through 3 different balloons. And you can see how they collapse. So this balloon here didn't really notice that it's dead. So it still has a usual shape. Here you already have a part of it that is missing. This balloon is already half destroyed, but probably because of inertia, this part is still keeps the old form. The other one already does a kind of crazy movement. And as I said, things like this are hard to predict, but with the measurements, it helps you to understand. Maybe in a model, you would have the idea, okay, it could happen like this, it could happen like this, 5 different reaction paths, how you would be able to destroy such a balloon, but then the measurement gives you the answer, which one is the right one. And that's a situation which you see quite often in physics or in chemistry. And using flashes of light not in the microsecond domain, but in a much shorter domain, femtosecond pulses, actually Amit Sevile did something similar. He looked at molecules destroyed by light. So he tried to understand what transition states you have in a certain chemical reaction. And he did it using femtosecond pulses. So you initiate a reaction and you want to know exactly what is happening there. Like always, chemists usually don't have simple, easygoing answers. Yeah, it could be reaction path 1, reaction path 2, and so on. And he could solve the question which model in reality is used simply by doing measurement with femtosecond pulses. And that brought him the Nobel Prize. Okay, it's only a Nobel Prize in chemistry, not in physics, but I think it's better than nothing. So let's have a look at the different timescales that we are talking about. So here you can see the detection time of humans. There we are in the second few tens of milliseconds regime. And if you want to resolve faster and faster events, you need then shorter and shorter flashes of light to do so. In the nanosecond regime, you are talking typically about gigahertz. That's something where still you can do electronics and so on. If you go to the picosecond regime, you can then study reactions that happen in chemistry. If you go to the femtosecond regime, you go even one step further. You can understand what happens in combination, recombination of electrons. So this is really the kind of natural atomic timescale that you can investigate. So with ultra-short pulses, you have a couple of things that you can do. On one side, you have this advantage that you can have a look at fast events. That's the first one. You can access ultra-short timescales. And that's something quite interesting. On one side, you can understand things. On the other side, you can also use it for doing fast things, like, for example, in optical clocking, intercommunication or so. You actually want to operate in gigahertz or tens of gigahertz regime, and with optics, you can do this. The second is that because you have flashes of light, you can actually concentrate the energy. And you can concentrate the energy in time, but if you have a laser, you can even go a step further and concentrate also the energy in space. And this way, you can create intensities which are extremely high. That's something that allows, on one side, for nonlinear effects. You can go to nonlinear effects which are so high that when you shine light on something, you simply completely destroy whatever you have. You can even rip apart all electrons from an atom simply by light. So that's one area. The other one is that you can also simply use it for manufacturing. You can do material processing of nearly every material in a very precise way. Or in the scientific area, you can do it. You can use it for high field science. I will say later a few words about it. And then the third property, which we will not discuss today so much, which I will focus on in the next presentation tomorrow, that is that you have a broad optical spectrum and that you can generate a COM-like structure. You have a train of pulses. If you do the Fourier transform in the spectral domain, you have a COM structure, and this allows for quite a lot of things, not only in spectroscopy, but even in areas like the realization of atomic clocks with unprecedented precision. Okay, so why do you have all this? What is the key to the operation of an ultrafast laser? Well, it's the coherence. If you have a normal light source, in thermal light source, you can't do all what I've been talking about. You need coherent light in order to make extremely short pulses. And okay, let's have a look at the coherence. So laser light is coherence. The spatial coherence is something that we're very used to. For us, there is nothing strange that this laser pointer, we can send it over a long distance on one side, or that on the other side, we can also focus it to a very small spot size, creating high intensities. But on the other hand, you also have the temporal coherence, which you can realize, which is a big difference to compared to normal light sources. And here similar. So on one side, if you make the divergence very small, you can send light over long distances, or you have a high divergence and focus it down like crazy. You can do the same also with the temporal properties. On one side, you can generate a very, very, very narrow spectrum and then have a long duration. And on the other side, you can also generate an extremely short event, but then you have a huge spectrum. And this allows for the realization of ultrafast lasers, and also if you put it in an oscillator that you have a train of pulses for the generation of frequency comps. Okay, so let's have a look for a start at a continuous wave laser. So in a continuous wave laser, you have the gain element, you have your cavity, high reflector, output coupler, everything very simple. If you do everything right, have the great gain material, and in principle also put a filter that you only have a single mode operation, but that's details. You can make a laser that just has a single frequency oscillating in the cavity. And so you just have one of the possible longitudinal modes. So you have a standing wave pattern here of the field. And so you have the light that circulates in the isolator. The losses are compensated by the gain in the laser medium. The gain saturates to a level that compensates the losses. And then you just have your CW laser. Now, if you want to transform such a laser to a pulsed laser, what you have to do is simply add an additional element. And one of the very successful techniques for ultra-short pulse generation is not adding an active element, but a passive element. This passive element does something quite interesting. It simply has a higher transmission for a higher intensity or a higher energy, as you want. And that means that you have a certain gain, and but there is also the loss, and only when you have a pulse, so this is here the loss in red of this element, and then when you send a pulse through it, the loss will go down, and then you have the gain, which is always there. It's a saturated gain for solid state medium, so always the same amplification. And during this time here, this pulse can then win something, it can be amplified. All the other noise that is between the pulses, so here you have a timeline, this is a repetition rate in the cavity, there is not enough amplification, so if you have noise or something like here, it will simply die out because the losses are higher than the saturated gain. Over time, it is just gone. And so that's the mechanism of passive mode locking. You have a device, and starting of passive mode locking is another question. I don't have time to go into detail into this, but usually when you switch your laser on, you have some noise, you have some stronger spikes, which then in the end develop to a pulse which can oscillate. And then if you have multiple of those, you have a kind of survival of the fittest. Only one survives. The one that has the highest energy saturates the saturable absorber the most. And in this way, you then have gain advantage compared to all the other things happening in the oscillator. So in the lecture on Friday, I will show a little bit more also with a small simulation animation why we call this mode locking. The basic idea is, so here you have a single mode, and you just have then this standing wave pattern, so this is something oscillating. If you do this with a lot of modes, with a comb structure of modes, in the end you have a short pulse forming, which then circulates around in the cavity. But let's talk about this on Friday in detail. Okay, how does a very short pulse look like? So let's have a look at a 5 femtosecond pulse. This is something which you can generate from nonlinear optics or also from titanium sapphire lasers. And let's place this at a wavelength of 800 nanometers. So 800 nanometers at the speed of light, that actually, so if this is a space axis and we just freeze time for a moment and have a look then at the envelope and at the underlying electric field of the pulse, well, the oscillation frequency that we have is something, or the oscillation time, so wavelengths divided by speed of light, is something which is 2.7 femtoseconds, and that is pretty fast. So the pulse itself, you can see really the individual oscillations, and that's the envelope of it. And also one question that you can ask is, how can you place this within the envelope? Can you also place, for example, this maximum here in the middle? The answer is yes, clearly. That's a difference between phase and group velocities in the propagation. This will become important also for the discussion of the carrier envelope offset, which is actually this phase difference between the maximum of the envelope and the maximum of the underlying pulse, but different story. Okay, so you have your pulse, 800 nanometer wavelengths, so less than a micrometer, and this is now propagating. How does it look in space, in a three-dimensional space? Well, you have the speed of light typically, then your pulse, if you multiply these 5 femtoseconds by the speed of light, you end up with only 1.5 microns. So this is something that is extremely thin. In terms of focusing, normally if you want to send a collimated beam, you have a beam diameter of millimeters or something like this. So you have really a very, very strong disk, which is incredibly thin. And that then propagates through space at the speed of light. I also want to say a few words about a technique for mode locking, which is the most used ones in commercial laser systems for especially industrial applications. In basic science, you have another one, which is care lens mode locking, but I don't have the time to go into detail into this. But for many industrial class lasers, what you do is you use a semiconductor element, which does a saturable absorber behavior. So that means that the loss goes down for a pulse that you send on it. And so here you then have this element, which is a saturable absorber, used as a reflector, the gain and the output coupler. And so the pulse simply does a ping pong between these two mirrors. Each time you hit the output coupler, parts of its energy is coupled out, and that then simply gives you the pulse train that you have at the output. And this saturable absorber that is used in many lasers in industry is based on a semiconductor. So what you do is you make a mirror structure, which is just an alternating stack of quarter wave layers with different refractive indices. And then you put an absorber that you can saturate on top of it. The absorber, you can simply imagine it like a two-level system in the easiest picture. And if you have excited all of the absorber to the higher level, then the absorption will be bleached, and that's it. And in this way, if you look at a curve showing you the reflectivity as function of the pulse fluence, the reflectivity, that's a red curve here, will simply go up and up and up and up. And as semiconductor absorber, you can use different things. You can put in a lot of things into it. You can use quantum wells, you can use quantum dots, you can even have several layers of those, and this allows you to do an engineering of the wavelengths in which you want to operate. You can also, in this way, change a lot the behavior. Behavior like, for example, the time that it takes to recover the absorption. Also the total change that you have here in the reflectivity. So that's one of the important parameters. You then have a second parameter, which is how do you integrate this into the mirror structure? Because if you have your wave coming into it, you have a standing wave pattern here, and you can put it either in a maximum or in a minimum. And in this way, you can steer the field strength in the absorber section. You can also optimize dispersion and so on. So there are a couple of things what you can do. In the end, what you want to do is having a full control over the macroscopic parameter that you want to use for making your laser work. And the macroscopic parameters that are interesting are on one side the level where the absorber starts to be bleached. So how much energy do I need to shine on it that I have a significant effect that the reflectivity goes up? That's called the saturation fluence. Then you also have the overall change of the reflectivity, which is the modulation depth. You have a little bit of nonlinear losses here, which are always there, which you cannot saturate. That's something that you usually try to avoid as much as possible. And as always in life, if you shine more and more light on something, something other will happen than the effect that you want to have. And typically at one point you will get a rollover. In many cases it's caused by two-photon absorption. And finally you then also have the parameter of the recovery time. And all these parameters you can optimize it. And I would say nowadays for semiconductors, mode locking of solid-state lasers, for nearly all laser materials you can find the right parameters to mode lock them. It might be a pain, you might have to throw a lot of money at it, especially if you're working in somewhat uncommon wavelength regions, but it's feasible. And then for the pulses that you can generate, so let's go back to this picture here. So you have your gain and the oscillation between the two end mirrors. So what are the parameters with which you can characterize such a laser? Well, on one side is what is the repetition rate that you get? So what is the frequency if I'm putting myself here at a position? How much time does it need until the next one arrives? That's then given by the cavity round trip time. So that's then here the cavity round trip time. Then the other question is how much energy do you have in total? So if I look at intensity as function of time, what is then the integral here of the intensity? That gives me the pulse energy. The average power is given by how many pulses per second do I get. So that means pulse energy multiplied by the repetition rate. Then you also have the pulse duration, extremely important because it defines in which region of interaction with matter you are operating. And finally, the peak power. And in the frequency domain, so then this repetition rate, if you do the Fourier transform of this periodic train, you end up with a COM structure, basic Fourier analysis. And the COMs are separated by the repetition frequency, but there is also one frequency offset, which is called the carrier envelope offset. And that's actually then the difference between the maximum of the envelope and the maximum of the field. Quite important. Let's discuss on Friday on it. Now for real life, what do you want to do? Well, this always depends on the kind of application that you have in mind. In many cases, I would say what people want to have is as much power as possible at a repetition rate suitable for your application, as high pulse energy as they can get, as short pulse duration that they can have. Also then this leads to a very, very high peak power. And ideally, you want to have this for a low price. So let's then talk about ultra-fast, high-power lasers. So if you want to do high-power lasers, the main challenge that you are facing is thermal effects. In a laser, you're pumping with photons that have a higher energy than the photons that are coming out. That's a normal way. You have some strange things where you can do it differently, but but that's a different story. But so normally you have then a big thermal effect which is happening in the gain material. So you're pumping, for example, at you're pumping at 808 nanometers, you're lasing at 1 micron, and you have a quantum defect of 20%. And this gives you then a heat problem with which you somehow have to live. This heat is deposited in your gain material, and this somehow limits you. And in order to overcome this, you need to figure out solutions that can do it. Now, why are you interested in going to high power levels? Well, there are two main directions. One direction is from the industrial side. So in the industrial side, what you want is you want to use a source with which you can drive a real process. And a real process means that you don't only want to produce 1 unit per hour or something like this. You need enough units that you can produce to make the whole process competitive to other processes that you can use. So with lasers, you can manufacture, I would say, nearly everything. You can remove material at an extremely precise level. The big problem is that quite often with ultra-fast lasers, it is also slow. What you can do, for example, is you shine a short pulse. So I showed this picture here. So such a pulse, the energy is concentrated in an extremely short time frame, femtosecond or picosecond level. And when you shine this light onto something, it is absorbed in the top layer, but then the light is already over. And typical thermal processes in materials have time constants which are relatively slow. You're talking about picoseconds, tens of picoseconds or more. If you shine a femtosecond pulse on something, put a lot of energy into it, then the atoms will simply rip apart. You destroy the chemical structure, and there is no time for the energy to go into the medium. So that means that you can manufacture more or less anything without problems. And even better, you have the possibility to manufacture things with lasers which otherwise would not be accessible. If you have transparent materials, for example, like the screen of a cell phone, if you want to do something there with visible light, you have a problem. But if you use short pulses, you can have multiphoton processes, and these multiphoton processes allow you to have also a good absorption. And cell phones are actually one of the big markets why now you have ultra-fast lasers entering an industry and being used quite a lot. Or another thing is, for example, here you can see fuel injection nozzles. There you want to do extremely fine and precise holes, ideally even with a conical structure. And this is very hard to do with standard methods. And by using lasers, you can have a better fuel efficiency if you do everything right. Or another thing here stands biomedical materials, you can manufacture them at a very, very precise level. Now, for making the process attractive from a commercial point of view, what do you want? Well, usually you simply want as many devices produced as possible in a short time. That means that you need sufficient energy to drive the process, to make the holes. You need also sufficient peak power, and you want to be fast enough so that you have a high enough repetition rate to drive the process. And this leads to the requirement that in the end you need also high average power. If you have a laser which has only a watt or so, for many processes it's not good enough. You want much, much more, tens of watts, hundreds of watts. And then another driver for high-power ultra-fast sources is science. And in science, I would say one of the hot topics is the area of high-field science. So areas where you have light intensities in the area of 10 to the 14th watt per square centimeter. And there you have the possibility to take out electrons from isolated atoms, accelerate them, bring them back, do generation of new frequencies, understand really what is happening in the shell of the electrons, and that's something quite hot. Now, in many cases, you have to integrate a lot of different effects. If, for example, you rip apart an electron, you generate a photoelectron and you want to look at it, you need to integrate over many different electrons. If you take several at the same time in a too close area, you then have some interactions between them and you can't resolve exactly what you want. So quite often you also want to go to higher and higher repetition rates in order to then resolve individual events. And so there is a quite strong drive today to develop sources which operate at high repetition rates. So this is a diagram. Sorry, I just need to drink a little bit of water, as we are not allowed to have a break. Okay, so here is a diagram, pulse energy versus repetition rate from somewhat older paper, 2008. And at that time, you had a quite strong separation between two classes. On one side, you have the oscillators, so simply ping pong between two cavity mirrors. And on the other side, you have amplifiers, so you take these pulses and amplify them in an additional gain medium. And there, what you typically did was you reduce the repetition rate from the megahertz, which is kind of the natural operation time for an oscillator. So if I have an oscillator of 1.5 meters, this gives me a repetition rate of 100 megahertz. If I go for 15 centimeters, the ping pong happens faster. Then I so 1 gigahertz gives me a nanosecond round trip time, and that's then only something like 15 centimeters. Now, the limit at that time was mainly given by the gain materials for short pulse generation, and also the pump sources, which only allowed to get a certain amount of power out of it. And so if you multiply repetition rate with the pulse energy, you get the average power. If you do it in this diagram, you simply have constant lines here. So this is a line of 1 watt of average power, 10 watt, 100 watt, 1 kilowatt. And at that time, most of the sources were limited to less than 10 watt of average power, at least in the commercial world. And there's then this high drive to go into the region where you combine the higher repetition rate with also higher pulse energies. But this means that you then enter regimes where you need average power levels, which are in the 100 watt regime or even in the kilowatt regime. And that is a challenge that you have to overcome. So the challenge, as I mentioned in the introduction, is the heat removal. You have the quantum defect and you need to get the heat out. If you put heat in a transparent material, unfortunately, you will see things like thermal effects, thermal lensing and so on. So you need a way to remove it in a controlled way. You can live with a little bit of thermal lensing, but you have to know what you're doing, how to get rid of it. And the successful techniques that allowed to go to kilowatt class power levels are actually based on trying to find systems which have a great surface to volume ratio. So you need to get the heat out. That means that if you have a large surface and something small inside, small volumes, it's easy to cool. And there are 3 techniques which have been really the big success stories for high power lasers. One is a fiber. In a fiber, you have the gain in a relatively small confined region. You also have the effect of the wave guiding. And then you simply make it very, very long, and in this way can easily cool it from the outside. Then the second geometry is to use a slab laser. So there you reduce the size of the gain medium. You can use it in different configurations in a single pass, or also quite often what people like to do is a zigzag pass inside the slab crystal for amplification. And then you simply make it sufficiently thin, cool it from the end facets, and in this way have also a situation in which you can remove the heat. And then the third geometry is the one of the thin disk. So it goes in the direction of a slab, but in a slab what you do is you have a propagation in the long direction. In a thin disk laser what you do is you make something which is very thin, cool it also, but then have a propagation of the light in the transverse direction. So the light only propagates to very thin layers of gain material. Now, that's the thing that you have to do if you are targeting high average power. If you're targeting ultrafast combined with high average power, then you have another challenge, and that's a challenge that you have to reduce the nonlinearities. So there are several methods what you can do. So why are nonlinearities bad? Well, on one side, if you have a lot of material and you have a very strong pulse propagating through it, you have nonlinear effects. And one of the nonlinear effects is that the refractive index can depend on the intensity. In the middle of a Gaussian pulse, you have a higher intensity. If this gives you a stronger refractive index, you will have a focusing effect. It's like a lens. In the middle, you have more material than at the sides, so you're focusing. And if you do this, you can easily destroy your medium because you start with a certain beam, and then it focuses a little bit and gets smaller and smaller and smaller, and crack, you need a new laser crystal. Now, one possibility is to operate at reduced intensities, and the other is to go to reduced interaction volumes. I don't want to tell too much about the way how you can operate at the reduced intensities by using chirp pulse amplification. I'm pretty sure that Andreas will talk in detail about it. But the idea is basically that you have the spectral, you have a certain spectrum, and you can divide the spectral components in time. So in one case, all the colors are happening at the same time. On the other side, you can also have them separated in time. First, the blue part of the spectrum, then the red part of the spectrum, for example, and in this way make it in the time domain very long, but in the spectral domain still sufficient, and afterwards you can recompress it. That's why you have then stretcher, which takes a pulse which is short, makes it long in time domain by separating the different colors. And then you amplify it without having trouble in the fibers that you get too many nonlinearities, self-focusing, and so on. And afterwards, you compress it and get your high pulse. This has been driven to the kilowatt level in fiber amplifiers. There are a couple of groups in the world who really did a great job, especially the one of Jens Limpert and Andreas Tünnermann in Jena. So they really have been driving this to completely crazy power levels. Also, the group of Furman and Galvanauskas also had pretty impressive results in these areas. Then there's the other approach, taking the slab. And in the slab, you can then do also, if you want this chirp pulse amplification, you can try also to design it, operate with slightly longer pulses that you don't need it, and then have such a multipass system. Here you can also go to the kilowatt class. Now, what I'm going to highlight is in such a chirp pulse amplification system, you still need an oscillator. So you still need something which typically has the saturable absorber element, the gain element, and so on, dispersion compensation. And so this is something common that you have, and afterwards you do all the amplification. Well, actually, the nice thing about the third part, about this thin disk laser approach, is that this is a technology which you actually can scale to very high power levels directly from the oscillator. And that's the focus of the work that I'm going to present right now. So here in such a CSEM mode-locked thin disk laser, so here you can see a picture. Here you have the disk with a pumping scheme. I will talk about this in a minute. And then you have the CSEM as one end mirror, and afterwards you have the output coupler here. And in between you just have ping pong on some mirrors. You need mirrors for dispersion compensation. Dispersion leads to the fact that the pulse can be separated, so blue before green or something like this. Let's talk about it a little bit later. Let's first have a look at what happened with the pulse energy of such ultrafast oscillators based on the thin disk approach as function of time. So here you can see the average power as function of time. And in this diagram, only two gain materials are shown which so far reached the highest power levels, ytterbium YAG and ytterbium lutetium oxide. So if you look at thin disk papers and so on, basically all of the gain materials for ultrafast are based on ytterbium because it's a great material. You can construct very efficient lasers based on it. And then depending on what material you put it in, you can have some interactions with a lattice and in this way broaden the emission spectrum. And that's what you typically try to do. You want to have some interactions and in this way have a large bandwidth because, as I showed initially, if you want to have a short pulse, you need spectrum. And if you make the spectrum larger, so if you put more and more and more and more and more lines, make it not only 1 nanometer but 10 nanometers or 100 nanometers, then you can make the pulse shorter and shorter and shorter. So for an example, 1 nanometer of bandwidth at 1 micron gives you roughly a picosecond. So that means that you need roughly 10 nanometers if you want to go to the 100 femtosecond regime. Okay, let's go back here. Okay, so this is a linear scale, and I have to say that I'm somewhat a little bit sad because when I was doing my PhD and we realized the first mode-locked thin disk laser, we are so proud of it. It was 16 watt average power in sub-picosecond pulses, which at that time was a big deal. I mean, at that time, normal ultrafast lasers had power levels of I don't know, 100 milliwatts or something like this. And so it was some quite good improvement. If I now look at the scale, actually this looks like the 0 point. So there was really some pretty good development over the years. And so now we actually arrived at a level where we have 300 watts out of such an oscillator. And this is actually the cavity setup of the actual oscillator that generated these 275 watts. So it is very simple. If you compare it to amplifier systems, the normal amplifier systems that I've seen so far at least have a relatively high degree of complexity. So with the oscillator concept, you can do it quite simple. Okay, there are a couple of drawbacks, but let's talk about this a little bit later. Then the second one also, if you look at the pulse energy that you can get out of such a system, it is also quite impressive. So initially we were talking about microjoules, and this was already good enough to do some really good nonlinear optics. So here on this scale, 1 microjoule, you can't see it. But with a microjoule pulse in sub-picosecond duration, you can already do a very, very efficient frequency conversion, as I will present a little bit later. But nowadays, we arrive at energies which are in the 80 microjoule regime. So hundreds of microjoules are, in my opinion, just a question of time until we get there. Okay, so how does the whole system work? What are the challenges that we have to overcome? Okay, challenges for high power operation. So mode-locked laser in principle is very simple, at least if you draw it in such a simple picture. You have the saturable absorber, the gain, and then your cavity. And if you also are not interested only in getting the average power high, but the pulse energy high, what can you do? Well, it's not very difficult. The repetition rate depends on the length of the cavity, and the pulse energy depends on the repetition rate. Quite often what you have is you have a certain pump diet that you can afford, let's say a 500 watt pump diet, and then you know you get a certain efficiency for the mode locking process. With this, probably you will be able to get 150 watt mode locked, and then you can choose how to distribute it. So if you have a repetition rate of 1 megahertz, or let's say a repetition rate of 3 megahertz or 100 megahertz, the average power is somewhat limited by the other components like the gain element and the pump. And then you simply can make the cavity longer so that you have a longer round trip time, and in this way get much higher pulse energy out of it. Your application has to be compatible with it, that's clear. Now, what are the challenges that you are facing? Well, on one side, you want to have the TM00 operation. So you want to have a fundamental Gaussian mode. This is something I don't want to go into detail, but it's mode locking because you are coupling the different longitudinal modes in phase together. And if you look at a normal cavity, you have also higher order modes that you can place there. But for normal cavities, typically these higher order modes are sitting at different frequencies. And so if you have a TM01 mode and a TM00 mode oscillating at the same time in the cavity, and you try mode locking, things will be messed up. And so you just want mode locking of a single transverse mode and then of a couple of different longitudinal modes together. And typically you choose the TM00 mode because first of all, with this you can generate the highest intensities. Second of all, it's also the one that you want to use for applications. I mean, if you have a donut-like mode or a TM, I don't know, 05 mode where you have two strong wiggles at the sides, I don't know what you really want to do with this in applications. And so to get to this TM00 operation, you need efficient heat removal, a good cavity design, and a good gain material that has sufficient bandwidth to support the short pulses that you want to generate. And then you also want to form pulses, so you need something that is an absorber which can survive high intracavity intensities. And then you also want to avoid a lot of the mode locking instabilities which can happen. One of the most prominent ones is Q-switch mode locking instability. What is happening there is that it's a kind of a feedback problem that you have in such a laser. The saturable absorber is an element which recovers kind of immediately after your pulse. If you do it right, you have picosecond recovery time. Let's say I have a 1.5 meter long cavity, 100 megahertz. So right after the pulse propagated over it, it is back to its initial state. And it has a property that the reflectivity goes up with higher pulse energy. Now in the gain, if you take a typical solid state gain material, you have lifetime of the gain, which is hundreds of microseconds. So a really, really long time. That means that it has its response. The gain is kind of flat for a long time. You have pumped it before. It is clipping to the level of the losses that you have in your laser. And it will not change quickly. And now what happens if you do a perturbation of the laser? Well, let's imagine that the pulse gets a tiny little bit stronger in terms of energy. The saturable absorber will say, hey, great, I can be more saturated. So initially, it will allow for a higher energy. The gain will say, I don't care. I have a lifetime of very, very long. So I don't change in a short time. And initially, this pulse will exponentially grow until at a later point, the gain saturation, because you're only pumping the gain with a certain amount of power, will set in and say, okay, you're taking too much average power out of me, I'm not happy. And then either you have something which is just a damped oscillation and everything is fine, or if you do it wrongly, you first have a big rise and then you get into a Q-switch regime. And that's the one that you want to avoid. And that's also why this CSEM, the semiconductor absorber, was such a big success, because here you had the possibility to optimize all the different parameters so that you can overcome this instability. But okay, this is a small side topic. So basically, for high power, we need this TM00 operation and we need a good pulse formation. And so first challenge is this fundamental mode. Despite the high thermal load, you need the good gain material, which has a sufficient thermal conductivity and also a good geometry. So as I said, fiber, disc, or slab are the really good ones. And so in the disc laser, what is really the principle in detail? So what you do is you have a disc, which is maybe just 100 micrometer thick. You are soldering it or gluing it onto a heat sink, which is well cooled, and you're using it with beams that have a diameter of millimeters or even centimeters. So much, 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 much larger than the thickness of the disc. And this concept was developed by Adolf Giesen from the University of Stuttgart in the 90s. Now, because you're doing this, you have a one-dimensional heat flow. The heat simply wants to go into this heat sink in a linear way. For a thermal lens, the things that kill you are actually gradients which are in the transverse direction. And this is something that you simply can avoid. You have 100 micrometer, very long distance in this direction. So all these sections here at a certain distance from the heatsink have the same temperature. You have a very strong gradient, yes, but only in the direction towards the heatsink, but not in the transverse direction, which kills your laser operation. And so let's have a look how the disk then looks in detail. So you have the disk, typically 100 microns, AR coating on one side, anti-reflective coating, highly reflective, both for the pump and the laser wavelengths on the other side. And then you can either glue it or metallize it and then solder it to the heatsink. So the heatsink, so this is now the disk here. That's an example which is a real-world system contacted by some people in Hamburg with whom we're collaborating, Günter Huber's group. And so then you simply have water streaming onto it. Here you have a little bit of copper and then the disk. And this is the basic concept of the thin disk laser. Now there's one problem that you are facing in such an approach. That is that for the materials you are interested in, for the solid state gain materials, typical absorption lengths are in the range of millimeters. That means that if I send now a pump beam onto this disk, if I send 100 watt onto this disk, and it's only 100 micrometer, probably I will get 95 watt or so just reflected. I will not absorb the power there where I want to have it, and the laser will be horribly inefficient. How can you overcome this? Well, the idea of Adolf Giesen was, well, then we simply recycle the unabsorbed pump. We send it again over the same disk. And that's what you can do. So you have here inside a parabolic mirror, and then the disk, and the light, the pump light comes from this side. And so in a single pass absorption, you, depending on the doping and thickness and so on, you only have 8 to 15% of absorption. But then if you make a pump module with, well, typical are 24 or 32 passes, you can nearly absorb everything. So you can go to levels of 98% of absorbed light and get very high efficiencies. And the other advantage that you also have is because you recycle the pump a lot of times, you have quite low demands on the pump brightness. So for ytterbium, it's not a wonderful 4-level system, it's a quasi 3-level system. You want to operate at a high pump intensity, a pump brightness in order to be able to build an efficient laser. And you can do it in this concept because you recycle the non-absorbed pump and in this way deposit the energy actually in a very small volume. Now, how does it look like? So here you can't really imagine how you steer these different passes through it. So let's have a look at a movie where it's shown more in detail. Okay. So that's a movie that was, okay, just 1 second, let's go back. Okay, so here you can see such a thin disk, what is happening inside such a thin disk module. So here you have the disk on the heatsink. This is a parabolic mirror, and you're sending the pump light from the fiber in a collimated way onto this parabolic mirror. And then it's sent many, many, many times over the disk. So you bring it onto the disk, and you have some back reflectors which bring it to another position. Here you can see this. And in this way you arrange your pass for, I think here what is shown is for 16 passes. This animation was, by the way, done by my postdoc Martin Hoffmann. Yeah, so many passes, we have to wait a little bit until it's finished. And here you have a back reflector so that afterwards you have then again the other passes. You box it, put your laser mirrors around the CSEM and the output coupler, and it's lasing. And so very simple to set up and easygoing lasers. Especially my PhD student Clément is laughing at this, but okay. In real life, it's a tiny little bit more complicated, but the basic level of complexity is not really that horrible. Yeah, so in this way, you can solve the challenge of the TM00 operation at high average power. And but in order to be able to do this, you also need a material through which you can send the power sufficiently well and which can also stand the deposition of a quite high power density. So if you have, let's say, a kilowatt of pump power and you have a centimeter-sized disc but only 100 microns, you're really depositing a lot of heat inside the material. And for this, then you need some good properties of the material. So you need good thermomechanical properties which allow you for the manufacturing of high-quality discs of only 100 micrometers. You need then also to contact them correctly and to use it afterwards also in the right cavity. Now, the best material that you have for thin disc lasers in terms of power levels is the material ytterbium yak. It's one of the first ones for ytterbium which has been developed, and it's used in numerous commercial systems. Actually, the whole thin disc technology was developed for high power lasers for remote or for applications in material processing. So the killer application which really made this technology a big success was the remote welding. What you want to do there is, so in the automotive industry, you want to, for example, manufacture door for a car in a short time, and you need to put a couple of welds on it. In the old days, what you had to do is you take a robot arm, and because the beam quality of the laser was so bad, you had to bring the robot right there where you wanted to place the weld. So that then takes some time because you have to move the robot arm over a distance. It was not able to have a small spot size with a lens which was far away because the beam quality was so bad that then the exiting beam would have been really huge. But if you go for a higher beam quality, so low m squared, you can have a reasonable opening, but still have very small foci, even at a distance of a meter or more. And that allowed then for remote welding applications, where they then had the kilowatt class lasers, but at a larger distance, sanding very quickly with a scanner on the different parts. And you can, I think they had at least a factor of 10 or so in productivity out of it. So that gave the need for developing solid-state laser systems with higher beam quality, and that then drove the whole development of the thin disc laser. Trumpf Laser in Germany, I think it's still the largest company for industrial lasers and laser solutions for manufacturing, pushed this technology. They have now thin disc lasers, continuous wave, multimode, but not as high multimode as other solutions in the program with, I think, up to 16 kilowatt of power. So this is quite incredible. I mean, if you want to cut steel, even at very thick dimensions, it is not a problem to do this with such lasers. And so ytterbium yak was developed for this. So you can buy today large discs which are on diamond, which have excellent quality. This is actually an old result with 1.1 kilowatt nearly fundamental mode. I'm not sure if this is still the current limit. I think they even went further to it, but I need to verify it, or if it was slightly multi-mode with 4 kilowatts. But so it's really possible to get extremely high power levels in good beam qualities from thin disc lasers. On the other side, if you're talking about ultrafast, if you look at the bandwidth, that you can obtain from ytterbium YAG, it's good, but not really excellent. In high power operation, in C-cell mode locking, the bandwidth is limited to, yeah, let's say a few nanometers, 2 nanometers or even less. And that gives you a duration which in high power operation is typically 600 femtoseconds, 700 femtoseconds. If you go for care lens mode locking, you can drive it a little bit further down in high power operation. There you're talking about 300 femtoseconds or so, but it's not good enough for what you would like to do. And that's why many, many groups are investigating different gain materials now. Here you can see a diagram of average power as function of the pulse duration for different ytterbium gain materials or ytterbium thin disk lasers in mode locked operation. So you have YAG, you have tungstate crystals, you have sesqui oxide crystals like lutetium oxide or lutetium scandium oxide. And so there are really a couple of different ones. Here, I don't want to go into detail about this development of new materials. You can already get, in terms of pulse durations which are in the 50 femtosecond regime. That's then from this material Calgo, which gives you a very broad and also flat emission. The problem is that if you look at the average powers right now, the power levels are going down for the shorter pulse durations. And that's why I would say at least 5 to 10 research groups are working on the question how to get into this regime where you combine power levels in the 100 watt regime with sub-100 femtosecond operation. Okay, then you have the second challenge, which are the nonlinearities. And so inside the laser, you always, for short pulses, will have some nonlinearities. The nonlinearities, the main nonlinearity that you see is SPM, cell phase modulation. And if you have cell phase modulation, depending on the chirp of your pulse, you control the direction of the bandwidth, optical bandwidth generation. So either you create additional spectral components or you take them away. You can find a solution where if you put the right amount of dispersion, you have a solution for which you can have a stable propagation. And that means that you simply need to figure out the right amount of cell phase modulation and dispersion, and then everything is fine. You can get a soliton that is propagating inside your medium. Typically, the changes that you're doing are quite small. You only have a few tens of milliradian or something like this of SPM for a whole cavity round trip. Now, when we initially tried to go to higher pulse energies, so for example, one possibility is, so I said initially, making the cavity longer allows you to go to higher pulse energies. Now, if you do this, you keep the average power constant, you should increase the pulse energy. But when we tried to do it, actually we saw that we don't understand what is happening here. The pulses are breaking up, we get multiple pulses, everything behaves strangely. While I was doing my PhD, the main conclusion was, well, this negative dispersion, we typically put it in with some dispersive mirrors. And we just said, okay, the manufacturers of the dispersive mirrors, they are crazy, they are not giving us good things. If I want negative dispersion, I need to put some resonance or something like this into the structure. And then I have material, and maybe this gives us additional SPM because we had way too much. The soliton formula did not work. Pulse duration as function of SPM and dispersion was not right. And so we just thought, okay, problem of the mirrors, that's it. Well, in reality, what it was something different. We actually completely neglected something which for most lasers is also neglectable, and that is the air inside the cavity. So if you look at air, the nonlinear coefficient of air for cell phase modulation is about 1,000 times lower than the nonlinearity of glass, for example. And so that means that typically in nearly all lasers you can neglect it. But if you look at a thin disk laser, well, basically in a thin disk laser, everything is in reflection. Let's go back to the simple picture here. Reflection, 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 reflection. Okay, here you have a Brewster plate, but you put it usually in a huge beam diameter, or you use a thin film polarizer. And the only element where you really have to go in is the thin disk, but also there you only have about 100 micron, okay, times 4, because you are using it in a folding geometry, so 4 times per cavity round trip, but it's clearly less than a millimeter of material that you have inside the laser. Now, if you look at a cavity of this type where you do a lot of ping pong in a Harriet cell to make the cavity very long, so here you are now talking about a Harriet cell which gives you additional 23 meters of cavity length. Well, if you have a millimeter of glass and then you have meters, several meters of propagation in the air, then suddenly the contribution of the air to the SPM becomes something that is important. And that was something that we initially didn't realize. After we realized it, we simply did something, we simply put a box around this laser, scotched it with, put a lot of scotch tape around it, trying to make it vacuum, helium tight, which is actually a quite stupid idea because helium goes away very easily and we had a large consumption of helium, which also cost a little bit of money, and we also had fun playing Mickey Mouse and but okay, that's a different story. And we then could increase the pulse energy initially to 5 microjoules and then afterwards to 11 microjoules, simply because helium has a much lower nonlinearity, so a 400 times lower nonlinearity. And then in the diagram, pulse energy versus time, so we could get to this dot here. So the first laser with which you could, oscillator with which you could get more than 10 microjoules. Now, that was one approach to do this. Another approach, which was quite a great idea, was to have it differently. So what we do here is we have a multipass cell giving us a cavity length. We have just a single pass on the gain. The gain is quite thin, so the overall gain factor that we have is not very high. So typically in such a configuration, the output coupling rate here is 10%. That means if we have 10 microjoules out here, we have 100 microjoules inside the oscillator. I think in this case we had even, I have to look it up, but I think it was even 140 microjoules or so inside the cavity. But so we have a factor of 10 enhancement in the cavity compared to the outside. And that makes it hard for us to avoid this SPM problem. So what the people in Thomas de Corsi's group in Constance, in collaboration with the people from Trumpf did, was a great idea where they simply made it different. They made a multipass cell, but this multipass cell also contained the thin disk as a mirror. And in this way, they could increase the gain many, many, many times. So actually in their system, they were then able to have 40 microjoule of output, and I think 40 microjoule of output for 70 microjoule inside the oscillator. And so the 70 microjoule, because they also put GTI mirrors, so dispersive mirrors, everywhere inside this multipass cell, they could put enormous amounts of dispersion inside the cavity. In our system, we had something like, I think, 10,000 femtoseconds squared or something like this, or 20,000. Here they had, I think, 300,000 femtoseconds squared. So they went to the limits that you can introduce with dispersion. They made it such that the pulse energy here is much lower because they have such a high degree of output coupling, 70% of output coupling compared to 10%. And in this way, then they could reach 40 microjoule in 145 watts. And finally, but this is kind of the limit that I would say which is reasonable, if you put too much SPM per cavity round trip, you get into a regime where then you act on the spectrum, where you get Kelly side bands, where the whole mode locking becomes more critical. And also if you are already coupling nearly everything out, so 40 microjoule out, 70 in, the potential for going much further is not so high. So then the other option is, well, either staying with helium or even simpler, you can also simply remove the air. And that is maybe the slight drawback that one can say that you have for these high power oscillators. Yes, the oscillator, if you look at it, it's actually quite simple. But if you really want to go to highest power levels, then you have to place it in vacuum or helium or something like this. But so with this helium box here that you can see, it's quite massive. If you see it in the lab, so it's I'm not allowed to leave this area, but it's, I would say, from here to over there, so a little bit more than half of this table. It looks somewhat like a submarine. You can flip it up, close it down. The only thing that when we designed it, we didn't find a good solution for it is actually when you flip it down, right now you would destroy the fiber here. So you first have to take the fiber for the laser out and later plug it back in again, but that's a difference. Yeah, that's not so important. Size is 0.9 meters by 1.6 meters, so still relatively compact. And then with this vacuum approach, we could get the 275 watts or also the 240 watt with 80 microjoules, optimizing for the maximum energy. And I have to say that, yeah, I'm a little bit surprised. I put this talk together yesterday evening, and I thought that I would go a little bit faster through it. Now we are 5 to 10, so I would say that could be a good moment to stop and simply say, why don't we stop the discussion here and simply do the other points on Friday, and I make, yeah, so we are still then in this ultra-fast high power sections. Okay, but that was also the largest part. And then we discuss the compression, the nonlinear applications, and also the frequency comps on Friday, so that we still have 5 minutes at least for questions.